In this lecture, we are going to discuss convolution in preparation for building convolutional neural networks. Of course, given the name, it's pretty obvious that a convolutional neural network is a neural network with convolution. And so, in order to understand CNNs, we must first understand convolution. First, I want to mention that people sometimes treat convolution as this mysterious thing. But as with our discussion of machine learning, we want to take the dumb as possible approach. Sure, convolution can be complex. It's a central operation in signal processing and computer vision. But in fact, it's quite simple. There are only two requirements. First, can you add? Second, can you multiply? If your answer to these two questions is yes, then you understand convolution. Believe it or not, convolution is just adding and multiplying. So let's start by not doing any math. Let's just look at convolution qualitatively. With convolution, there are three objects you want to pay attention to. First is the input image. Second, there's the filter. Note that another name for the filter is the kernel, so we're going to use those two terms interchangeably. Finally, there's the output image. The output image is what you get when you convolve the input image with the filter. In other words, if I perform the convolution operation on the input image and the filter, I get the output image. The mathematical symbol for convolution is a star or asterisk, not to be confused with the asterisk that we use in computer programming for multiplication. So if you're writing convolution in code, it will not be an asterisk because in code, we already use the asterisk for multiplication. It's helpful to think of some examples of convolution to understand what it can do. There are two examples I really like. The first example is blurring. So the input image is just the original image, and the output image is a blurred version of that image. You might recognize this operation from applications such as Photoshop. The second example I really like is edge detection. As input, we have the original image, and as output, we get white lines where there are edges in the original image, and we get black where there are no edges. So the output image highlights all the edges in the original input image. So that's your first lesson on how to view convolution. This perspective is that convolution is an image modifier. The input is the original image, and the output is a modified or transformed version of that image. In other words, you might think of this as a feature transformation on the input image. You know, that sounds curiously like what a neural network does. In any case, what makes blurring and edge detection actually work if they are both convolution? What makes one convolution different from another convolution? Well, the answer is the filter. When you use a Gaussian filter, this blurs the image. When you use an edge detection filter, you get edge detection. You can think of that as sharpening the image. Your next question might be, how do we find or design these filters in the first place? That's something we'll discuss later in this section, but the answer, as you might have come to expect, is just another dumb as possible approach. Okay, so let's get into the nitty-gritty of how convolution works. I promised you that all you need to know is how to add and multiply. Let's see if that's true. We're going to use very tiny images for this example, although in reality, the actual images we work with will be much bigger. This is just so we can feasibly do these calculations by hand. So let's start with an image 0, 10, 10, 0, 20, 30, 30, 20, 10, 20, 20, 10, and 0, 5, 5, 0. And we also have the filter 1, 0, 0, 2. So how do we convolve this image with this filter? Let's imagine overlaying the filter at the upper left corner of the image. Then all we need to do is element-wise multiplication and add up all the results. So we get 1 times 0 plus 0 times 10 plus 0 times 20 plus 30 times 2. that is equal to 60. This gives us our first output in the output image. And as promised, all you needed to do was multiply and add. Now let's move our filter over one space to the right. And then let's do our element-wise multiplication and add up the results again. So we get 1 times 10 plus 0 times 10 plus 0 times 30 plus 2 times 30. That's 70. This gives us our second output, which goes to the right of the first output. Now let's move the filter over one more space to the right and do the same operation again. We get 1 times 10 plus 0 times 0 plus 0 times 30 plus 2 times 20, and that's 50. This gives us our third output, which goes to the right of the first two outputs. Now you realize that there's no more space to move our filter to the right anymore. So let's instead zigzag back to the left, but go down one row. And then let's repeat our calculation. We get 1 times 20 plus 0 times 30 plus 0 times 10 plus 2 times 20. That's equal to 60. This gives us our first output in the second row. So you can see that the output location corresponds to where we've placed the filter along the original image. So we're not going to go through the rest of the calculation since that would be a bit redundant. But what I want you to do is, if you don't understand this, do the rest of the calculations by hand to make sure that these results are correct. So we have 60, 70, 50, 60, 70, 50, and then 20, 30, 20. One helpful exercise to get a better idea of how convolution works is to write pseudocode and even real code to implement the algorithm we just described. This will help us uncover a few hidden details you may have not considered. Just by starting the code, you realize one thing you need to take care of, which is, what size should I initialize the output array as? If you recall, in our example, the input image had length 4, while the kernel had length 2. The output had length 3. So what's the pattern? I claim that if you have an array of length n and a filter of length k, then there are n minus k plus 1 distinct possible positions you can put the filter into. You might want to draw this on paper if you don't see right away why this is true. So the first step in our pseudocode is to initialize the output array. But here's another detail you may have not considered. The output height will be the input height minus kernel height plus 1. The output width will be the input width minus kernel width plus 1. But in our example, both our image and kernel were square. So you might be wondering, is this always the case? What's the convention? And the answer is that for images, usually these are not square. This just has to do with cameras and screens. Most screens, like your computer screen and your TV screen, are not square, and therefore cameras do not take square pictures. Therefore, images we find in the wild that we want to use as data are typically also not square. Some neural networks do use square images for convenience, so when you build a data set, you make them square. And one example of this is MNIST, which we've already seen. On the other hand, kernels are almost always square by convention. Let's move on. The next step is just to fill in the output array by performing the convolution algorithm. So first we loop through 0 up to output height with the index I. Inside that, we loop through 0 up to output width with the index j. So the pair ij will always index our output. Then we loop through each position of the kernel. So we have ii going from 0 up to kernel height, and we have jj going from 0 up to kernel width. Finally, inside all these loops, we have our main calculation, which as promised is just multiplication and addition. We multiply the input image at position I plus ii, j plus jj, by the kernel at position ii, jj, and we add this result to the output image at ij. Now it's okay to accumulate using plus equals because we initialize the output image to be all zeros. As an exercise, you might want to try and put this into code so that you can confirm that it works and returns the expected result. The inner part of this pseudocode is key because it helps us understand the equation that defines convolution. So here we can see that the ijth entry of the output, a convolved with w, is the sum over I prime and the sum over j prime of a at I plus I prime j plus j prime times w at I prime j prime. Now you might ask, why are we looking at these complicated equations if PyTorch already does all this work for us? And the answer is that this will help you immensely in understanding the different perspectives on convolution that we are going to discuss later. Moreover, if you're a curious person and you go on Wikipedia to read about convolution, you'll see something very similar to this. In this example, you can think of x as the filter, y as the input image, and z as the output image. Now you might notice something weird about this equation from Wikipedia, which is that instead of plus signs, we have minus signs. Why is that? Is the lazy programmer wrong? And the answer is, in fact, all of deep learning is wrong. But for better or worse, that's just the way we do things. In the end, it doesn't make a difference because the filters we use will be learned using gradient descent, in other words, automatically. So the process of finding the filter will be done automatically using gradient descent, which will find the best values that optimize our loss function. So it doesn't matter if the filter is reversed or not. In fact, if you use a library like SciPy, you'll notice that it already has a function called convolve2d. The problem is, if you use this function as is, you'll get a totally different answer than we did. And as a side note, you might want to try that yourself to confirm that what I'm saying is true. Now, this is because convolve2d does a proper convolution and not the deep learning version of convolution with plus instead of minus. In order to make SciPy's convolution work the same way, we have to flip the filter both horizontally and vertically and set the mode argument equal to valid. Now, as a side note, convolution is a commutative operation. A convolved with W is the same as W convolved with A. Therefore, it doesn't matter which input we flip. In fact, what we are doing in deep learning is actually known as the cross-correlation. I actually think this is a much more helpful and descriptive name compared to convolution. Convolution in and of itself probably doesn't mean much to you, but the word correlation does. You probably think of the word correlated as sameness. So if I say x and y are correlated, that means to you that there's some degree of similarity between x and y. Therefore, you might think of CNNs as a correlation neural network rather than a convolutional neural network. The only difference between correlation and convolution is that convolution reverses the orientation of the filter, whereas correlation does not. The final topic I want to talk about in this lecture is this mode argument. To understand this, it's helpful to look at these animations, which kind of summarize how convolution works. Basically, you're sliding the filter across every possible position in the input image. In this animation, the motion of the filter is bounded by the edges of the image. Because of this, the output image is always smaller than the input image. But you might wonder, what if I want the output image to be the same size as the input image? In this case, what you can do is add padding. This is equivalent to adding a virtual array of zeros around the input image, so that the filter can extend out to those values. The reason I say it's virtual is because you wouldn't really want to allocate this space in code. There's no reason to, since you already know that anything multiplied by 0 is still 0. So in other words, to quote-unquote add padding, you can just pretend there are zeros surrounding the input image. As many zeros as you need to ensure that the output size is equal to the input size. You may have noticed, however, that even with padding, we still lose some information. What I mean by that is, there are outputs we could calculate. If we extended the padding even further, that would be non-zero outputs. So another thing you can do, which is not as common these days, is to extend the padding further so that you can catch all these non-zero outputs. This results in an output size of n plus k minus 1 if your input image has length n and your filter has length k. Again, you should draw this out on paper if you're not convinced this is true. To summarize the three modes of convolution, let's look at this table. The first one we discussed was called valid convolution. This applies when the kernel can only touch the original input image. The output size is n minus k plus 1. The second one we discussed was called same convolution. In this scenario, we add some padding, just enough so that the output size is the same as the input size, n. The third mode we discussed is called full convolution. In this scenario, we extend the filter out as far as possible so that at least one point on the filter overlaps with one point on the input image. The output size is n plus k minus 1. Normally, in deep learning, we use valid or same convolutions. In this lecture, we are going to look at a Colab notebook that does image classification using PyTorch with a convolutional neural network on the CIFAR10 dataset. This lecture is going to walk you through a prepared Colab notebook, although a very good exercise, which I always recommend, is once you know how this is done, to try and recreate it yourself with as few references as possible. As usual, you can look at the title of the notebook to determine what notebook we are currently looking at. Alright, so there are a few major differences at the start of this code. First, you can see that the imports are almost the same as before, except that we also import torch.functional. You'll see how that will be used very shortly. I like to introduce these new things when there's not much else going on, so that you can learn about different ways of doing the same thing, which could be useful in the future. Next, you'll notice that we're importing the CIFAR10 dataset, which is a color image dataset and is even more difficult than FashionMNIST. However, since the dataset is included in Torch Vision, loading it in is just as easy as it was for the previous two datasets. Next, let's look at the raw data by calling the data attribute. As you can see, it's slightly different from MNIST and FashionMNIST, which return torch tensors. Instead, CIFAR10 is stored as a regular NumPy array. And the D-type is UN8. Next, let's check the shape of the training data. We can see that we have 50,000 training samples, and each training sample is a 32 by 32 color image. Next, let's check the targets. This is again different from MNIST. Instead of being stored as a tensor, it's stored as a list. Next, let's get the number of classes k by adding all the targets to a set and then taking the length of that set. Next, let's create our data loader objects, which is the same as how we did it before. As mentioned previously, here's a good opportunity to look at one of the quirks of PyTorch. If we look at the shape of the data yielded by our data loader, we see something interesting. The batch that's yielded by the data loader has shape 1 by 3 by 32 by 32. This should seem strange to you because now the color channel comes before the spatial dimensions instead of after. PyTorch hides this detail from you by getting you to use data loaders and special dataset functions. Next, let's look at our CNN custom model class. You'll notice that this is built a little differently from our previous CNN. What I'm trying to do is show you different ways of accomplishing the same thing. One thing that's different is the number of input color channels, which is now 3 instead of 1, since our data is in color. Next, you'll notice that in the constructor, I've only defined layers that involve parameters, so there are no ReLU activations. So where did they go? Well, remember that none of these layers are actually called until we get to the forward function. So let's look at the forward function. We can see here that instead of treating the ReLUs as modules or layers, we can treat them like functions, which can be accessed from torch.functional. That's the new thing we imported earlier, if you recall. In fact, dropout can be applied this way as well. You can also see here an alternative way of using the view function, which, as you recall, flattens the data. Instead of putting the -1 in the last dimension, we can put -1 in the first dimension and then specify the second dimension explicitly. This isn't any extra work for us because we had to calculate this value anyway inside the constructor. So you can see 128 times 3 times 3, both in the constructor and in the forward function. Alright, so next is a bunch of stuff we've seen before, so I'm going to skip over it a lot faster. So we instantiate our model, we move the model to the GPU, we create our loss and optimizer, we do our batch gradient descent loop, and we can see that our model trains quite fast at around 6 or 7 seconds per epoch. If we look at the loss per iteration, it seems to look okay. Next, we check the model accuracy. So we get about 75% on the train set and a 66% on the test set. Of course, this is going to vary depending on several different factors. So when you run this, you might get a slightly different answer. But clearly, this is a much more difficult data set than MNIST or Fashion MNIST. Next, we look at the confusion matrix. In fact, there are so many things that we predict wrong that it's kind of difficult to look at. We can see that we confuse 1 and 9 a lot. 1 corresponds to automobile and 9 corresponds to truck. This makes sense and fits our intuition. We can see that 3 and 5 get confused a lot. 3 corresponds to cat and 5 corresponds to dog. That makes sense, especially when you consider that these are very small pictures. We can also see that 0 and 8 get confused a lot. 0 corresponds to airplane and 8 corresponds to ship. That makes less sense, and perhaps it could simply point to the fact that our model is just not powerful enough. So if we scroll down to the bottom and we look at some misclassified samples, maybe we can make sense of these results. So here's a horse predicted as an airplane. That does not make sense at all. Here's a bird predicted as a deer. That kind of makes sense. Here's a truck predicted as an automobile. That kind of makes sense. Here's a cat predicted as a bird. Looks like a small blob, so that kind of makes sense. Here's a frog predicted as a deer. That doesn't really make sense. Here's a dog predicted as a cat. That kind of makes sense. Alright, so it seems that a lot of these wrong predictions, the neural network should be able to get right. So in the coming lectures, we're going to see how we can improve this model. In this lecture, we are going to discuss how to improve our model using a process known as data augmentation. Consider this picture of a cat. You and I can agree that it's a cat. Now consider this other picture of a cat. It's pretty obvious that this is the same cat. Unfortunately, while this is easy for us, it's not so easy for a computer. Now, the neural network may be able to identify this because of convolution, but perhaps there's a way to help the neural network learn this translational invariance using data augmentation. As you may have heard, one of the reasons deep learning has been so successful these days is that we have so much more data. Deep learning continues to improve as it trains on more and more data, while other machine learning algorithms seem to hit a plateau. One disadvantage of tabular data is that you just have what you have. If we're doing classification to see if you'll pass my math exam, and I base that on how many hours you study and how many hours you play video games, that can only depend on the data I collected through my survey. I can't just make up new data, which would necessarily include my own biases about student performance. I can't invent a new student who studied this much and played video games this much and then decide if he passed or failed. That wouldn't make any sense. However, images are an important class of data. We can see them. We know that both these images are cats. I know that if I rotate this cat a little bit, it's still a cat. I know that if I flip a car upside down or left to right, it's still a car. Although you should probably be worried if you encounter an upside down car. In other words, what I'm trying to say is, with images, it is okay to invent new data. Now, here's one problem with this approach. Data takes up space. So the more new data I invent, the more space it takes up. And on top of that, there are an endless number of ways I can invent new data. I can shift the image to the left 1 pixel, 2 pixels, 3 pixels, 4 pixels, 5 pixels, and so forth. And I can also go in the other direction. I can also rotate 1 degree, 2 degrees, 3 degrees, and so on. Do I really want to store all these combinations on my hard drive? Probably not. Also, Google Colab probably wouldn't have space for that anyway. So what can you do? Luckily, none of this work is work you have to do yourself. Have you ever considered how to rotate an image? Well, it's not as straightforward as it sounds. Instead, we can use the Torch Vision API to do all this work for us. To understand how it's going to work, we have to discuss the concept of generators and iterators. For the purpose of this lecture, we won't really differentiate between the two. Consider what you do when you want to write a for loop using indices 0 up to, let's say, 10. We would do for I in range 10. Now in Python 2, you would not want to use range 10 because that would return an actual list of numbers from 0 up to 9. Instead, you would use xrange, which does not create a list, but rather generates those numbers on the fly. That's why in Python 3, this is the default behavior for the range function. If you print out range 10, you will not see a list of numbers from 0 up to 9, as you might expect. Conceptually, that's what it is, but physically, that's not what it is. Instead, it just says range 010, which is kind of not telling us much. A range is a range. Well, it appears to be some kind of object, on which you can call instance methods and so forth. What you might not have known is that you can actually write your own generators. For example, suppose you wanted to write a loop where the loop variable was a randomly generated number. So for x in my random generator would be a loop where on each iteration of the loop, x would be a random number. Can we do this in Python? The answer is yes. We can accomplish exactly this using the yield command. So here is how you would write a myRandomGenerator function that generates 10 random numbers on the fly. As you can see, the code to generate the entire list of values does not have to be computed beforehand. And more importantly, the entire list of values does not have to be stored in memory. Instead, this takes up a constant amount of memory because as soon as the variable for each iteration is computed and used, it is no longer needed. So in PyTorch, when we want to do data augmentation, it's a similar concept. Instead of pre-calculating all of our augmented images beforehand, we are going to create them on the fly. You can imagine that it looks something like this. For each batch of data, we augment X batch using some randomly generated values. Then we yield X batch and Y batch. In other words, only a small slice of X train is ever augmented on each iteration. More importantly, it's done randomly, so you get something different each time, which helps with generalization. What you should notice is that this looks curiously like our data loader, which we have already used for generating batches when we do batch gradient descent. So how does this actually work in PyTorch? What we've learned so far in this lecture is just conceptual. Practically speaking, the answer lies in the functionality we have already been making use of. Specifically, you know that when we load in the CFAR dataset, it's just a function, and this function accepts as input an argument called transform. At this point, you should ask yourself, I wonder what this does. In addition, as you may recall we learned in the last section, the data loader object yields your dataset in batches as you loop over it, applying the transform function on the fly. So to be explicit, what we have to do is modify the transform argument and instruct Torch Vision on how to augment the data. Specifically, Torch Vision comes with a whole collection of different transformations you can apply, such as slightly changing the color, cropping, flipping both horizontally and vertically, rotating, and so forth. I like the idea of changing color because I don't think people mention it that often, yet it seems very important. You would want your model to perform well under different lighting conditions and different colors. I would recommend checking out the documentation and experimenting with each of them in different combinations to get a feel for what has the most impact on your particular dataset. As I mentioned early on in this course, PyTorch gives us a lot of building blocks from which we can compose more complex things. Just like how we can compose complex neural networks from simple layers, we can also compose complex transformations made up from these basic ones. All we have to do is wrap them in a torchvision.transforms.compose object and pass this into the transform argument when we load in the data. Now, because all of the data augmentation transformations are specified in the data function itself, that means everything that happens after that does not need to change. Specifically, consider what the data loader would look like. Exactly the same as before. All the instructions for transforming the data belong to the dataset object itself, not the data loader. If you recall, the only thing that the data loader does is call the transform function on the dataset. Similarly, we should expect that the training loop also does not change. We still have a nested for loop to do batch gradient descent. The first loop is still for I in range epochs, and the second loop is still for inputs targets in data loader. The only thing to be careful about is that while you do want to augment the training set, you probably don't want to augment the test set. Otherwise, you get a different answer each time you evaluate it, which is undesirable. After all this, you might still have one remaining question. So far, we've loaded all our image data from pre-built functions in Torch Vision. But what if we have our own image dataset? Sure, I can load images into NumPy arrays using a library like Pillow. But once I've done that, how can I apply these transformations that Torch Vision provides? It seems like in order to use them, I must have a Torch Vision dataset object. Luckily, we will cover this later in the course, but for now, you'll just have to wait and see. In this lecture, we are going to introduce a new type of layer, which has been shown to be very helpful in training convolutional neural networks. Here's something to consider. Recall that early on, we looked at why it's important to normalize your data before passing it into a model such as linear regression or logistic regression. We do this by subtracting the mean and dividing by the standard deviation. But because this is an operation on the data, we can only do it at the very first layer of the neural network. What happens if the data becomes not normalized at some later layer? Then that layer has to deal with unnormalized data, which is not as good as normalized data. So this begs the question, how can we make the data at every layer normalized? The answer is batch normalization. If you recall, inside the PyTorch training loop, we're actually doing batch gradient descent. On the outer loop, we loop through each epoch. And on the inner loop, we look at a chunk of data on each step and do gradient descent with respect to just this chunk of data. This works because we know that a batch of data will have approximately the same statistics as the full dataset. So what if we did something like this? We inject a layer that does normalization for us. For example, in an ANN, instead of dense, 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 we have batch norm dense, batch norm dense, batch norm dense. At each of these layers, all it does is take the batch of data, subtract its mean, and divide by its standard deviation. In fact, this is pretty much what batch normalization does. But there's something extra that batch normalization does. Here's another question to consider. How do we know that normalization is actually good? In fact, we don't. Perhaps there's a better amount of shifting and a better amount of scaling that we can use that leads to a more optimal model. And so this is the full description of the batch normalization layer. It first does normalization using the batch mean and the batch standard deviation. Then it rescales the data and reshifts the data so that the final output has an optimal location and an optimal scale. Of course, these new parameters, gamma and beta, are learned automatically using gradient descent. One alternative perspective on batch normalization is that it acts as a regularizer. As you know, we use regularization to prevent overfitting with methods such as dropout. So how does batch normalization do regularization? The idea is, because each batch of data is slightly different, it's going to have a different mean and standard deviation. It's not the true mean and standard deviation of the entire dataset. These differences are like noise, which slightly change what the neural network sees on each iteration. In other words, because the neural network always has to learn noisy images, it becomes impervious to the noise. The final thing I want to mention in this lecture is that, while we discussed batch norm in the context of a feed-forward neural network, batch norm is not commonly applied in between dense layers. As you recall, this is the CNN section of the course. And so the reason we're talking about batch normalization now is because batch norm is mostly used with convolutions. Now, adding batch norm also adds some hyperparameter choices. In particular, you have to decide whether or not you should use batch norm. And if you decide you should, then you have to decide where to put it. Luckily, we can just follow the conventions in this regard. Batch norm layers are usually applied after convolution layers. Well, after or before depends on which way you look at it, so maybe a better way of looking at it is that they go in between convolution layers. One common pattern would be like this: convolution to batch norm, to convolution to batch norm, back to convolution, back to batch norm, and then flatten, and then your dense layers. So that's just to give you an idea of what it might look like. You're always encouraged to try things on your own, but also to read about the most popular CNNs, such as VGG, ResNet, and Inception, to see how they're doing things. This is the approach we're going to take in the next lecture when we improve our CFAR 10 results. By the way, if you want to read more about batch norm, you can check out the paper included in extrareading.txt. The title is Batch Normalization: Accelerating Deep Network Training by Reducing Internal Covariate Shift. In this lecture, we are going to improve our previous results using some of the techniques we just learned about, including data augmentation and batch normalization. This lecture is going to walk you through a prepared Colab notebook Although, a very good exercise, which I always recommend, is once you know how this is done, to try and recreate it yourself with as few references as possible. As usual, you can look at the title of the notebook to determine what notebook we are currently looking at. One important feature of this notebook is that it has many options for you to choose from. We've added quite a few things since the last script. So as an exercise, one thing you want to try is experiment with what happens if only some of these options are used and not others. For example, check the results when we don't have data augmentation. Check the results when we don't have batch norm. Check the results if we remove one layer of convolutions. This is part of the process of improving your results in hyperparameter optimization. Okay, so at the top, you'll see that when we load in the dataset, we specify a transforms.compose instead of just a transforms.toTensor. This is a list of things I tried, and you definitely want to play around with these to see if you can improve the results. There are tons of things here, and each of these things has its own parameters, so test them out and see what happens. So pretty much everything in this script is the same as the previous CFAR10 script, so let's just scroll down to where we build the model. Okay, so here we're just inspecting the data. Here's the data loader. Alright, so here's where we define the model. The first thing you'll see is that I've taken away the strided convolutions. In this scenario, for these small images, normal convolution followed by max pooling actually seems to work better. But also, we're taking inspiration from the VGG network, where they do multiple convolution layers before they do pooling. Now, VGG is designed for much larger images, so it's also a much larger network. They actually have 5 groups of convolutions and poolings, and each group has multiple convolutions. 2 in the first couple layers and 3 in the following layers. So that's another thing we've done differently. First, convolution with no strides, and now multiple convolutions before doing pooling. Initially, you might want to try only this by itself to see how it works. The next thing you can see that we've added is a batch norm layer after every convolution. Not much to say here since we just described how and why it works. But as I mentioned before, because I added so many things to this script, you want to turn some off and turn some on in different combinations so you can see for yourself the effect each of them has. You'll notice that for these convolutions, I've used padding equals 1. This is because I wanted to show you how to achieve same padding such that the output image is always equal in size to the input image. Basically, we can take the formula from the PyTorch documentation and plug in values for the kernel size and stride. Then we use the fact that we want h out to be equal to h in, and then we can solve for p. In this case, I get p equals 1, so that means if we want same mode convolution, then we have to use padding equals 1. This makes convolutional arithmetic a little easier for us. After each convolution, the size of the image remains the same, and after the max pool, the image is downsampled by 2. So basically you can take 32 and divide it by 2 3 times. We end up with 4, so the size of the input of the first linear layer is 128 times 4 times 4. Finally, we have our final dense layers with dropout, which is the same as before. Alright, so let's scroll down. So we instantiate the model, move the model to the GPU, create the loss and optimizer, do batch gradient descent, observe our losses. So these epochs take a little longer, around 15 seconds, and also notice that we did 80 epochs instead of just 15. Alright, so here's the loss per iteration. Something you may have noticed in the previous script is that it had some overfitting, and you can see here that the overfitting effect is less. So let's look at the accuracy. And you can see that we reach much higher accuracy than before. So now we get about 94% on the train set and 87% on the test set. Next, let's look at the confusion matrix. Alright, so this is encouraging because a lot of these off-diagonal numbers are a lot smaller than before. You'll notice that a few of them are still quite high, such as when we confuse 3s and 5s, which are cats and dogs. I think this is the most difficult to discriminate in this dataset because in a 32 by 32 image, cats and dogs are going to look extremely similar. We also still see a lot of 1s and 9s being confused, which correspond to automobiles and trucks. Again, that seems to make a lot of sense. Okay, so let's take a look at a few misclassified samples. So here is a cat predicted as a truck. That doesn't really make sense. Here's a truck predicted as an automobile. I think we can agree that that might be a truck. Here's a cat predicted as a horse. We can kind of see how that might be a horse or a dog. Here's a frog predicted as a cat. So this frog is kind of in the same pose as a cat might stand in. Here's a horse predicted as a deer. So again, we can kind of see why that might be. Here's a truck predicted as a ship. Personally, I don't think it looks like anything. Here's an automobile predicted as an airplane. So that seems kind of wrong. It looks like a car. Here's a horse predicted as a deer. That seems to make sense. Here's a dog predicted as a horse. That kind of makes sense. So all these four-legged animals are very hard to distinguish, at least for a neural network. Here's a bird predicted as a horse. If we look closely, it kind of looks like a bird. And we can definitely tell it looks more like a bird than a horse. But if you weren't told the label, you might not even know what it is. So I think it's clear that while we improve the performance of the neural network, it still doesn't reach human-level image recognition capability. One conclusion you can draw from this lecture could be summarized as bigger is better. We've seen that by virtually adding a lot more data to our dataset and using a much larger neural network than what we've seen so far in this course, we were able to significantly improve the performance of our network on this dataset. This is a very common theme in deep learning, and it's often surprising because it seems so simple. The fact that it's so simple actually makes it seem less profound than it really is. Some people believe that, instead of better algorithms, we just need to scale up our data and our models and our compute, and this by itself will lead to breakthroughs in AI. As noted, our final neural network in this lecture is much larger than what we've worked with so far. In general, CNNs can get pretty deep, even hundreds of layers. This is a big jump from the last section, when all we had was just 2 dense layers. At this scale, it helps to be able to see a summary of your model in some way. And so the Torch summary library allows you to do just that. By calling the summary function and passing in the model and input size, you get a table that shows every layer in your model, along with some other useful information, such as the output shape and the number of parameters in each layer. So first we have our initial conv2d layer, which has 896 parameters, and its output shape is 32 by 32 by 32. This is because we used same mode convolution. We can do a quick sanity check to make sure that the number of parameters makes sense. Our filter is 3 by 3 by 3 by 32. That's because it has 3 input channels, its size is 3 by 3, and it has 32 output channels. And so 3 times 3 times 3 times 32 is 864. Then we have the bias term, which is a vector of size 32. So 864 plus 32 is 896, which checks out. If we scroll down to the end, we can see the total number of parameters in the model. For this neural network, it's about 2.4 million. So again, a big jump from what we were working with previously. In this lecture, we are going to continue our discussion of convolution by looking at a totally different perspective on how it works. This is very helpful for understanding convolution, but it doesn't teach you anything new mechanically. So this lecture is optional if you want to move on and just learn about how to make CNNs. Something I mention very often is vectorization. We like to vectorize operations in code because using NumPy functions is a lot more efficient than writing your own Python for loops. The pattern you're looking for when you want to vectorize an operation is usually of the form of a dot product. A dot product is an element-wise multiplication and then the summation of those results. So whenever you see the sum over I of AI times BI, that's a dot product. This also applies to matrix multiplication, since if A and B are matrices, then the matrix multiplication of A and B is just A dot B. You'll notice that for convolution, we yet again have something similar. The only difference is that there are two summations. However, this is not really a relevant detail, since the outcome is still the same. Instead of summing over one axis, we're summing over two axes. But it's still an element-wise sum and add. The question is, why is the dot product important? One definition of the dot product, other than the element-wise sum and add, is that it's the magnitude of A multiplied by the magnitude of B multiplied by the cosine of the angle between A and B. We sometimes call this the cosine similarity or cosine distance, depending on the sign that you use. So how does this work geometrically? Consider just the angle for a moment. If the angle between the two vectors is 0, then the cosine of that angle is 1. That's the maximum value of the cosine. Now imagine that the angle between two vectors is 90 degrees. Then the cosine of that angle is 0. Finally, imagine that the angle between two vectors is 180 degrees. This is basically as far apart as possible. Then the cosine of that angle is -1, which is the minimum value of the cosine. So if you're just using raw cosine, then it's a similarity. The larger the number, the closer the two vectors are. The smaller the number, the further away they are. The maximum value when A and B are parallel is 1. The minimum value when A and B are anti-parallel is -1. And if A and B are orthogonal, then the cosine similarity is just 0. Okay, so why is that important? Consider now how you would find the cosine of the angle between two vectors. That's just A dot B divided by the magnitude of A and the magnitude of B. So I just rearranged the equation that we had before. Now, let's compare this to another popular measurement, the Pearson correlation. The Pearson correlation is defined as what you see here. But notice how similar this is to cosine similarity. The only difference is that the Pearson correlation uses mean subtraction. And so now you have two hints that convolution is really correlation. The first one from before was that we were actually doing what is called the cross correlation. And second, now you have that the dot product is actually very similar to the Pearson correlation. So I hope that by this point, you are convinced that the dot product, while it seems like an abstract concept, can be thought of as a correlation measure. It tells me how correlated is the first thing with the second thing. If they are highly positively correlated, then the dot product should be large and positive. That means two vectors pointing in nearly the same direction. If they are highly negatively correlated, then the dot product should be large and negative. That means the two vectors are pointing in nearly opposite direction. Finally, if the two vectors are orthogonal or at right angles, then the dot product should be 0. The reason why this is important is, you don't have to think of a filter as an abstract concept. In fact, it's just a pattern finder. This actually makes the term filter make a lot more sense. It filters out everything not related to the pattern contained in the filter by setting them to 0, and keeps everything that is related to the pattern. So what convolution is doing is, it's passing this filter along each point on the original input image and sliding it along. At each point, it asks, is the pattern here? Is the pattern here? Is the pattern here? And so forth. Then it gives us a high number in the positions where the pattern is found, and then a small number where the pattern is not found. And thus, this is your first alternative perspective on convolution. It's just a sliding pattern finder that passes through an entire image looking for a particular pattern. In this lecture, we are going to continue our discussion on alternative perspectives of convolution. Again, this is very helpful for understanding convolution, but it doesn't teach you anything new mechanically. So this lecture is optional if you want to just move on and learn about how to make CNNs. So in this lecture, what we are going to talk about is the equivalence of convolution and matrix multiplication. In other words, in what scenario are they actually the same thing? Let's do an example. This is easier to see if we only do a one-dimensional convolution, so let's first go over how that would work. This should be easy since two-dimensional convolution is just a generalization of this. So let's start with a one-dimensional image, A equals A1, A2, A3, A4. We also have a filter, W equals W1, W2. Then the convolution output will be B, which is A convolved with W, and the elements are A1 times W1 plus A2 times W2, A2 times W1 plus A3 times W2, and A3 times W1 plus A4 times W2. So in general, we can write one-dimensional convolution as the sum from I prime equals 1 up to k of A at I plus I prime times W of I prime. You'll notice that this is the same equation we had for two-dimensional convolution, just with the second index dropped. Using this, it's pretty easy to see how we would implement the same thing using matrix multiplication. What we've done here is we created a matrix where we repeat the filter along each row, but on each row, we shift it to the right by one space. Now, I recommend you do this by hand so you can see that it works. If you multiply the matrix by the original input vector A, you get the correct output of the convolution. So what's the lesson here? It's that by repeating the same filter again and again inside a matrix, we can implement convolution without actually doing convolution. Instead, we can just use matrix multiplication. But there is another problem with this particular method of doing matrix multiplication, and this is that the equivalent matrix repeats the filter multiple times. So the result is that the matrix takes up a lot more space than the original filter, which was just a two-element array originally. In other words, while this was a helpful perspective, you don't necessarily want to implement convolution this way. Instead, it's helpful to look at this from the opposite direction. What if there are instances where, instead of doing a full matrix multiplication, we can replace it with convolution? This is the idea behind parameter sharing or weight sharing. Think of it this way. Inside a neural network, we are constantly doing this operation, A equals W transpose X. Here, A is the output activation and X is the input feature vector. W is the weight matrix. Well, what if instead of a full weight matrix, we just had the same two weights repeating over and over again? Then we have less parameters, our neural network takes up less memory and RAM, and thus we can make the computation more efficient. In other words, convolution saves both space and time by using less weights. Why might we want to do this? Consider what we did in the previous section, where we had a fully connected neural network looking at a single image. Luckily, those images were just grayscale images of size 28 by 28, which gives us 784 features. But what if we had a slightly larger image and add color? The CFAR10 dataset is one such example. Those images are 32 by 32 by 3. In this case, we have 3,072 features. That's quite a large increase from 784. And keep in mind, a 32 by 32 image is quite modest in size, to say the least. Modern CNNs, such as VGG, look at images of size 224 by 224. If you used a full weight matrix, then you would have 150,528 features. Suppose you're looking at an image with modern HD resolution. That's 1280 by 720. In this case, you would have about 2.8 million features. As you can imagine, this is much too large for a neural network. But there is another good reason to use weight sharing, which is that you don't need different weights for each part of the neural network. Remember that convolution is actually correlation, and the filter is really a pattern finder. In this scenario, we actually want the same filter to look at all locations on the image. This is the idea behind translational invariance. Suppose we are building a dog versus cat recognizer. Here is an image containing a cat. Here's another image containing a cat. But what's the difference between these two images? The only difference is that the cat is in a different position. Now, if we used a fully connected or dense neural network, we would have to learn the weights for each of these positions separately. And on top of that, this neural network won't generalize well, because if we come across the same cat, but in a new position, the neural network would have failed to recognize it. So in fact, it's better to have a shared pattern finder, because this pattern finder looks at all locations on the image. You don't need to learn the weights to look at a cat at every single possible point, which would actually be infeasible. In this lecture, we are going to extend our understanding of convolution so that it looks a little more like what goes on in a neural network. First, remember that in general, a neural network accepts as input color images. We know that these are three-dimensional objects, height by width by color. But for all the examples of convolution we just looked at, both the image and the filter were two-dimensional. So how can we reconcile this discrepancy? Previously, we conceptualized an image as a square, and the filter also as a square. Then we would slide this little square along the big square and do a multiply add, and that's convolution. So if our image has 3 dimensions, we just go with the same analogy. Our color image is a big box, and our filter is a little box. Then we slide this little box along the big box, and at each position, we do a multiply add, and that's a convolution. Here are the details. At each position, we used to sum over the height and width of the kernel because the kernel was 2D. But now, since the kernel is 3D, we're going to sum over the color channel as well. Note that both the kernel and the image, for now, have 3 color channels. If you recall, that's red, green, blue. The way that you can think of this is that instead of the filter being a grayscale pattern finder, it's now a color pattern finder. Suppose the filter is looking for a red circle, so there's a circle in the red channel. Now, it's only going to match red circles. It won't match blue circles or green circles. This is opposed to the black and white filter, which has no color at all. If it saw a circle, then the pattern would be found. There's no concept of color in a black and white image. Ultimately, this picture is still not complete. Using what we just learned, this is what would happen. Our input image is a three-dimensional object, height by width by 3. Our kernel is also a three-dimensional object, k by 3. The output of this convolution is only two-dimensional, height minus k plus 1, width minus k plus 1. And this is because we're summing over all 3 dimensions. And so the third dimension kind of gets dotted out. Now, there's nothing necessarily wrong with the output being two-dimensional, although this should offend your sensibilities to a certain extent. Remember this idea of the uniformity of a neural network and how we have repeating structures. The feed-forward ANN works because you can add any number of layers. One dense layer followed by another followed by another. This is okay because the input and the output are of the same type. The input is a vector and the output is also a vector, which can then be the input into the next layer. But for convolution, so far this doesn't seem to work. If the input is three-dimensional, but the output is only two-dimensional, then we do not have this uniformity. We can't plug in the same kind of convolution right after the first one, since the input is not the same as the output. But here's a question to consider. Remember that the filter can be thought of as a pattern finder. So it's looking for a particular pattern, or in other words, looking for a particular feature. But we know that in machine learning, we have multiple features. Just like how each hidden unit in a neural network represents a different feature based on the inputs. That kind of makes sense. If we're looking at an image, we would want to identify multiple features in the image. For example, let's say you're building a facial recognition network. One filter might be looking for an eye, and another filter might be looking for a nose. So it makes sense then that if we want to find multiple features, we should have multiple filters to find them. So consider for a second what would happen if you had two filters acting on the same input image. Call the input image A. Call the first filter W1, call the second filter W2. The output of A convolved with W1 is B1, and the output of A convolved with W2 is B2. Let's say for simplicity's sake that we're using same mode convolution so that B1 and B2 have the same height and width as A. So if A is h by W by 3, then B1 is h by W, and B2 is also h by W. Now we have two outputs, B1 and B2, but with different features found in each. What should we do with them? Well, how about we simply stack them together? Now, all of a sudden, our output is three-dimensional. It's height by width by 2. And in fact, we can add any number of filters to find any number of features. So nose, eyes, lips, eyebrows, chin, so on. Now our input looks like our output. They are both three-dimensional. This means we can have multiple layers of convolution, one followed by the other, in a repeating pattern just like we do with ANNs. But of course, just like with the ANN dense layer, we want to vectorize this operation so that it can be done all in one go, rather than doing, say, 10 different convolutions and then stacking them together. So here is the formula that represents how to do a complete convolution in a deep neural network so that both the input and the output can be three-dimensional objects. Now, this is a lot to look at all at once, so let's try to consider each part one step at a time. First, let's consider the shape of everything. We know that A will be h by W by C1. You can think of C1 as the number of color channels the image A has. Then we have the filter W, which has the shape C1 by K by K by C2. Note that this is now a four-dimensional tensor. Then we have the output image B. Assuming that we're doing same mode convolution, the height and width dimensions will be the same, h by W, but the third dimension will be C2. So in our equation for the convolution, we can see that it's pretty much the same as before, just with more indices. Bijc represents the image pixel value at row I, column J, and color channel C. Note that I use the term color loosely here, because it doesn't really represent color anymore. We can have an arbitrary number of features, so C2 can be 10, 100, or 1000. Conceptually, however, we're still just doing what we talked about previously, just individual convolutions, which output two-dimensional images, and then stacking all those images together to get a three-dimensional object. So let's just summarize what we learned in this lecture, since that was a bit long. First, we started with realizing that we only define convolution for grayscale images, and with corresponding two-dimensional filters. This is of course not flexible enough for CNNs, which must accept color images as input. So then we said, okay, let's just extend that by doing a three-dimensional dot product between a color image and a three-dimensional filter with the same number of color channels. So we're dotting over the color channel. Next, we realized that this breaks uniformity, so we can't stack layers together to build a deep neural network. And this is deep learning after all, so we kind of need to be able to do that. And this is because when you convolve a 3D image with a 3D filter, you still get a 2D image as output. This is just like when you dot a 1D vector by another 1D vector, you get a scalar. So we extended this by realizing that we don't just want one filter that's going to find one single feature. We need to find multiple features. Therefore, we need multiple filters, which will output multiple 2D images, which of course can be stacked into a 3D image. Then we vectorize this operation so that both the input and the output are three-dimensional. Now you might be wondering, is it correct to call the final dimension color? That may be the case for the input into the neural network, which is always height by width by 3, but this breaks down at every other layer. For example, if you have height by width by 10, then the 10 dimensions don't really represent color. But as we discussed, conceptually, we're just finding different features in an image. So our terminology changes to cover this more general case. We call these feature maps. This makes sense because you can think of each 2D image as a map, as in a literal map you can look at, which is the result of a convolution with some filter which is looking for some feature. So this map is telling us where in the original image that this feature can be found. So just like a map. The final output is just a stack of all these different maps, one map for each feature. And so the size of the final dimension is referred to as the number of channels or the number of feature maps rather than colors. Finally, I want to talk about how convolution is going to look as a neural network layer. If you recall, you can think of convolution as just matrix multiplication, but with shared weights. And as you know, in a feed-forward ANN, we don't just have matrix multiplication at each layer. We do some other things as well. In particular, we can add a bias term and apply an activation function. Well, a convolution layer works the same way. We're going to add a bias term and apply an activation function. Because remember, this allows us to find nonlinear features or nonlinear functions of the input, which are more powerful than simple linear functions. Importantly, we have to consider what the shape of the bias term should be, given that the output of the convolution is a three-dimensional image. In a dense layer, if we have a vector of size m, then our bias term is also a vector of size m. In other words, there is one scalar for each element in the result. But for convolution, the bias term will not have the same shape as w convolved with x, which is a three-dimensional image. Now you might think, isn't this equation invalid if b does not have the same shape as w convolved with x? Technically, this shouldn't be allowed by the rules of matrix arithmetic. If we want to add two matrices together, they should have the same shape. Technically, this is true, but this is conceptual only, and this will actually work in code due to the rules of broadcasting. So the bias vector b is only one-dimensional, and it has the size c2 if w convolved with x has the shape h by w by c2. In other words, the same bias term applies to every pixel for each feature map. As a side note, convolution is generally a commutative operation, so it doesn't really matter if you write w star x or x star w. Although this is not entirely true in the deep learning case, since w is 4-dimensional and x is 3-dimensional. Nonetheless, this is just conceptual only, so let's pretend that w comes first so that it looks more like the dense layer equation. Alright, so now that you understand how convolution and a full convolution layer works in a neural network, let's consider our savings. Remember that one way to look at convolution is that it's parameter sharing. Sharing parameters means that we use the same weights in multiple places, reducing the number of total weights we need. So let's do a quick calculation to determine our savings. Suppose our input image is of size 32 by 32 by 3, a modest size image. Now let's suppose the size of the filter is 3 by 5 by 5 by 64, so there are 64 output feature maps. Then our output image will have the shape 28 by 28 by 64. This is because 32 minus 5 plus 1 is 28, and let's just assume we're using valid mode convolution. The number of parameters we needed to compute this output is just 3 times 5 times 5 times 64, which is 4,800. Now, let's compare that to the case where we would use a feed-forward neural network with a flattened image, like we did in the previous section. Then our input would be 32 times 32 times 3, which is 3,072. Our output again would be of size 28 by 28 by 64, which is 50,176. So if we use the dense layer, we would have a weight matrix of size 3,072 times 50,176, which is approximately 154 million. Now that's a lot of parameters for just one layer of a neural network. In fact, compared to using convolution, we have about 32,000 times more parameters. As you can imagine, this would require a huge amount of RAM and a huge amount of compute. It would take longer and would perform suboptimally because, as we stated earlier, convolution is a pattern finder. We use the same filter to find the same pattern in multiple places. Without shared weights, every weight needs to learn the pattern at every location the pattern could appear, which is suboptimal. This would be bad for generalization. Using this concept of convolution just being a part of a neural network layer, it's easy to see how we are going to find these convolution filters through the process of training. At this point, we've come quite a long way since our first introduction to convolution, where we had the perspective that convolution is just an image modifier. The examples we used were blurring and edge detection. We took an image and then convolution modified it in some way. But now we have a deeper understanding of convolution. It's in fact a pattern finder and a shared parameter matrix multiplication. It's just a feature transformer. In this way, it's just like the neural network layers we'd seen earlier in the course. And so having this perspective, it becomes pretty obvious how these filters, or feature transformers, will be found during the training process. The answer is that it's all going to happen automatically when we do gradient descent. This will update both the filter and the bias term as usual, and they just happen to be a different kind of operation than what we had in the linear layer. But conceptually, you know that whether you have a linear layer or a convolution layer, both of these are just multiplying and adding, so there should be no problems applying gradient descent as usual. Now that you understand how exactly a convolution layer works, including the bias term and activation function, we can now consider the architecture of a convolutional neural network and why it's that way. So, as a little bit of a history lesson, modern CNNs essentially all originated from the same model, the LeNet. This is named after Yann LeCun, one of the original deep learning pioneers, along with Geoffrey Hinton and Yoshua Bengio. What we're going to do in this lecture is just start with what the architecture is, and then go through it piece by piece so that you understand why it is the way it is. Okay, so let's look at a typical CNN. A typical CNN has two stages. The first stage is a series of convolutional layers. Importantly, these convolutional layers are usually followed by pooling layers, which is another type of layer we'll discuss shortly. The second stage is a series of dense layers, also called fully connected layers. These are just a regular feed-forward neural network as you saw in the previous section. If you recall, I said in the previous section that neural networks have this hierarchical structure. Each layer is always looking at features that were found in the previous layer. So you can even think of the first stage as just another feature transformer. It's a feature transformer that specifically works on images and finds image features. Then, once it's found those image features, it passes those into a neural network, and then the neural network does what it does best: nonlinear classification or regression. So let's have a closer look at the convolutional stage. Now, I just added a new layer without really explaining it, the pooling layer. Why would we want to do that? At a high level, pooling acts as a downsampling operation. What is downsampling? That's when you make a smaller image out of a bigger image. So imagine your image is 100 by 100. After pooling, if the pool size is 2, then you would get a 50 by 50. That's downsampling by 2. Let's go over mechanically how this works, and then we'll explain why it works and why we would want to include it in our neural network. So there are two kinds of pooling: max pooling and average pooling. Choosing which one to use is, as you probably guessed, a hyperparameter choice. Let's talk about max pooling first, since I think this one's a bit more common. The best way to see how it works is by example. So if we start with an image, let's say it's a 4x4 and contains these numbers: 1, 2, 3, 4, 5, 6, 7, 8, 16, 15, 14, 13, 12, 11, 10, 9. So just the numbers 1 to 16, but organized non-sequentially. What max pooling will do is take each 2x2 square, of which there are 4, and just return the maximum value in each of those squares. So the max of 1, 2, 5, 6 is 6. The max of 3, 4, 7, and 8 is 8. The max of 16, 15, 12, 11 is 16. And the max of 14, 13, 10, 9 is 14. So the output image is 6, 8, 16, 14. As you might have guessed, average pooling is similar, but instead of taking the max, we take the average. So for the same input image, we have the following. The average of 1, 2, 5, and 6 is 3.5. The average of 3, 4, 7, and 8 is 5.5. The average of 16, 15, 12, 11 is 13.5. And the average of 13, 14, 10, 9 is 11.5. So the output image is 3.5, 5.5, 13.5, 11.5. Now that you know how pooling works, let's talk about why we should use it. The first advantage of pooling is practical. If we downsample the image shrinks, and therefore we have less data to process, less multiplications to do, and of course that will speed things up. But the second and more important advantage has to do with image processing itself. Recall this idea of translational invariance. This is the idea that I don't care where in an image the feature occurred. I just care that it occurred. For example, both you and I can recognize this as an A. We also recognize this as an A. It doesn't matter where I put the A on the screen. So translational invariance is important from a biological point of view and how we as humans learn. We don't have to learn how to recognize A's at each point in our field of vision. Once we know what something looks like, we can recognize it, no matter if it's up, down, left, or right. So what is max pooling doing? Well, consider a small 2x2 box. Remember that convolution tells us whether or not a feature has been found. It's a pattern finder. So imagine that in this 2x2 box, I have these flags: pattern found, not found, not found, not found. So it's a high number and a small number and a small number and a small number. The pattern being found returns a higher number. So when I take the max, it says the pattern has been found. That's good because it tells me that the pattern has been found without caring where it was found. Average pooling is the same idea, but I think max pooling is a little more intuitive in this regard. As a side note, keep in mind that in this lecture, I've assumed that we're using a pool size of 2, and that at each pooling layer, we select boxes which are 2 spaces apart. Now, pooling layers have some flexibility in this regard. First, it's not necessary for the pool size to be the same in both directions. For example, you could look at a 2x3 box or a 3x2 box, although generally that's unconventional. Second is that it's possible for the boxes to overlap. The hyperparameter that controls this is called the stride. It tells us how many spaces to move the pooling box for each output. Previously, we looked at the situation where we had a pool size of 2x2 and the stride was also 2. This is a pretty common scenario. If you had a stride of 1, then our 2x2 box would overlap. This is not really too common. So while you have these options, which I want to make you aware of, they are usually not changed too often. So what you see in this lecture is what we do most often. We use a pool size of 2 in each direction, and we have a stride of 2 so that we don't have any overlapping boxes. So now that you know what pooling does and why it works, let's discuss why the convolutional part of the CNN is organized the way it is. Why should we have a sequential pattern consisting of a conv layer, followed by a pooling layer, followed by a conv layer, followed by another pooling layer, and so forth? If you recall, I told you earlier that one cool thing researchers discovered is that CNNs are able to learn features hierarchically. So the initial layers end up learning basic strokes, the next layer ends up learning individual facial features such as nose, eyes, and lips. The next layer ends up learning whole faces. The key point to keep in mind is that after each pooling, the image shrinks, but the filter sizes generally stay around the same. Common filter sizes are 3x3, 5x5, and 7x7. Generally speaking, they are much smaller than the input image. But what happens as the image shrinks as it passes through each layer? Well, let's suppose we start with a 32x32 image, and we have 4 convolutional and pooling layers. Let's assume we do convolution in same mode so it doesn't change the size of the image. And let's assume all our convolution filters are size 3x3, although this doesn't come into play just yet. In this case, after the first convolution and pooling, the image shrinks down to 16x16. After the second convolution and pooling, the image shrinks down to 8x8. After the third convolution and pooling, the image shrinks down to 4x4. And finally, after a fourth convolution and pooling, the image shrinks down to 2x2. What happens after this is still a mystery, so let's just leave that for now and focus on the image shrinking. As you can see, if you take a 3x3 filter and place it over a 32x32 image, it occupies only a very small portion of the image. In other words, it's looking for very tiny patterns to match, like for example, simple edges and strokes. Then the image becomes size 16x16. Now all of a sudden, the 3x3 filter takes up 4 times as much space in the image. It takes up twice as much space in each direction, and 2 times 2 is 4. In any case, it occupies a much larger portion of the image relative to the first filter. So now it's looking for patterns which take up more space on the image, patterns like nose, eyes, and lips. Next, we get to an 8x8 image. A 3x3 filter occupies almost a quarter of the image. After that convolution and pooling, we get a 4x4 image. Now, a 3x3 filter takes up most of the image. So what have we learned? We've learned that in a convolutional neural network, convolution and pooling results in 2 things which are corollaries of each other. First, the image input shrinks. Second, since filters generally stay the same size, the filter looks for larger and larger patterns in the image. This is what leads to the CNN learning hierarchical features of the input. It first learns things that are relatively small compared to the total size of the image. Then it learns to find bigger patterns and so forth. The last concept regarding the convolutional layers we have to think about is, are we not losing information at every layer if we shrink the image? And the answer is yes, that's true. We are losing spatial information because the image keeps shrinking. We're saying we don't care where in the image the feature was found, just that it was found somewhere in the image. So we're losing information about where it was. But there's another component of the convolution process we haven't considered yet, which is the number of feature maps. Again, we have a general pattern to follow, which is that while the size of the image generally decreases, the number of feature maps generally increases. In other words, I don't care where the feature is found, I just care that it was found. But I do care about different possible features I can find. So while you're losing spatial information, you're gaining information in terms of what features were found in the image. One last note on this convolution and pooling pattern. One of the hardest things to grasp for new students in deep learning is that we have so many choices. We call these hyperparameters. Previously for ANNs, we looked at the learning rate, the number of hidden layers, and the number of hidden units. But now with CNNs, we have a ton of more choices. With convolution, we have to choose the filter size, we have to choose the number of feature maps, we have to choose the pool size, and so forth. But luckily, I think this is one instance where there's a general pattern that most people follow, so you're not going in completely blind. So stick with these guidelines, and you can be sure that you're at least doing things per accepted convention. That is, choosing small filters relative to the image, like 3x3, 5x5, or 7x7. Another guideline is to repeat the pattern, convolution followed by pooling. Another guideline is to increase the number of feature maps at each convolution. So you might start with 32, and then 64, then 128, and maybe 128 again. The best way to learn about how other people are doing it is to read lots of papers and check out which hyperparameters they selected. Generally, you'll find that this is the pattern followed by most convolutional networks. Next, I want to mention something a little funny, but in fact, pooling is sometimes not what we are going to end up using in our CNNs. Researchers have found that we can do something similar, but which is more efficient and sometimes works just as well. In particular, recall that for pooling, we have this concept of stride. That tells us how far apart each box should be when we take the max. In fact, convolution has a stride option as well. So in this animation, you can see how convolution works with stride. Remember, convolution just means multiply and add with a sliding window. When we have convolution with a stride parameter, the stride tells us how far apart each window should be. And of course, our intuition tells us that if we use a stride of 2, then the output image length will be half of what the input was. In other words, we get the same reduction in size by using a strided convolution instead of convolution followed by pooling. The intuition behind why this works is that if you consider what an image looks like, an image is just large patches of stuff. What I mean by that is, each pixel is likely to have a similar value to its neighboring pixels. For example, suppose I'm looking at a red car. I find a red pixel. Now ask yourself, is the pixel above that also red? Yes. Is the pixel below that also probably red? Yes. The same can be said of the pixel to the left and to the right. That's just the nature of images. Pixels near each other are often very highly correlated. You won't have this random jumping around of pixel values because something like that wouldn't look like an image at all. That would probably just be noise. And so using a stride of 2 simply means having your filter skipping every other pixel. It's saying we don't care what those skipped pixels are because they probably are very close to the pixels we were already looking at. So to summarize, the convolutional part of our convolutional neural network now looks like this. We can have a series of strided convolutions, all with approximately the same filter size, with increasing feature maps at each layer. Or we can have a series of convolutions followed by pooling, again all with approximately the same filter size, and with increasing numbers of feature maps at each layer. The last part of this lecture will focus on the second half of the CNN, which is the feed-forward neural network part. Now there's not much to discuss here, except that we have to consider the shape of an image is not appropriate for a dense feed-forward neural network. Remember that when an image comes out of a convolution, it's going to be three-dimensional, height by width by number of feature maps. But a feed-forward neural network takes in a feature vector, a one-dimensional object. Luckily, we've already discussed how this works. We can turn a 3D object into a 1D object using the view function in PyTorch. One alternative to the flattened layer, which I really like, is the global max pooling layer. This is a little different from the regular kind of pooling we discussed earlier. Consider the question, what if we have different sized images? The largest source of images is the internet. Generally speaking, images we find on the internet are not all the same size. So it makes sense to wonder, is it possible to build a convolutional neural network that is capable of handling different image sizes? And the answer is yes, using a global max pooling layer. Let's consider first why a simple flattened layer would not work. Suppose again we have an input image of size 32 by 32 and 4 convolutions. Assume again we use convolution in same mode and we have a stride of 2. So after the first convolution we get a 16 by 16, after the second convolution we get an 8 by 8, after the third convolution we get a 4 by 4, and after the fourth convolution we get a 2 by 2. But now, let's say we have an input image of size 64 by 64. In this case, the output after 4 convolutions would be 4 by 4. Let's say for simplicity's sake, the number of output feature maps is 100. Then, for the 32 by 32 image, doing a flatten operation would yield an output of size 2 by 2 by 100, 2 times 2 times 100, which is 400. For a 64 by 64 image, doing a flatten operation would yield an output size of 4 times 4 times 100, which is 1600. And of course, a feed-forward neural network is not capable of handling vectors of different sizes. Now, let's consider how global max pooling works. The idea is simple. If our input image is h by w by c, then the output is 1 by 1 by c, or equivalently just a vector of size c. In other words, it takes a max over the entire image along the spatial dimensions over each feature map. Since we have c feature maps, we end up with what is essentially a one-dimensional vector of size c, since the one dimensions are redundant. This follows the same general idea of pooling, where we're saying, I don't care where in the image the feature was found, just that it was found somewhere. Global max pooling is the extreme of this, saying that the feature can be found anywhere in the entire image, across the entire height and width. Since the output is always a vector of size c, it does not depend on the size of the image, meaning that it allows the network to handle images of any size. As a side note, we also have global average pooling, which is just a global version of regular average pooling. The only exception to this is if your images are too small, in which case you'll just get an error when you try to run your code. For example, if your image starts out as a 2 by 2, then it's not possible to reduce the dimensions by half 4 times. You'll notice this happens if you do something like add too many convolutions to your neural network. Alright, so let's summarize the basic architecture of a modern convolutional neural network. The first stage is a series of strided convolutions, or optionally, convolution followed by pooling and repeating that pattern. In the interface between convolution layers and dense layers, we have a flatten. We also optionally have a global max pooling that reduces the image to just the max for each feature map. Finally, once we flattened our data into a one-dimensional vector, we have a regular feed-forward neural network made up of a series of dense layers as usual. And as you learned in the previous section, the activation and number of nodes for the final layer depends on the type of task being done. So if you're doing scalar regression, then you'll only have one output node with no activation function. If you're doing binary classification, you could have one output node with a sigmoid. However, for k equals 2 or more classes, you can have k output nodes with a softmax activation. In this lecture, we are going to begin discussing code preparation in preparation for our CNN notebook. This lecture will focus specifically on how we're going to build a model, since as we move to more and more complicated architectures, we'll need more and more sophisticated ways of building models. There will be two major components of this lecture. First, as you know, the critical new piece of math that makes an ANN into a CNN is convolution. So we'll see how to use the convolution module in PyTorch. Second, we'll need to integrate this convolution module into the neural network. I'm going to show you two ways of doing this, but the highlight will be the object-oriented method of building PyTorch models. So if you don't remember your object-oriented programming from your first-year programming class, now would be the time to crack open your old textbook and reacquaint yourself with those concepts. So number one, we want to look at the convolution module. The module we need is called conv2d, and on this slide, what I want to do is highlight its arguments and relate them to the math that we already learned. As you know, the main parameter in convolution is the filter or the kernel, which is a four-dimensional tensor composed of the number of input channels, the number of output channels, and the kernel height and width. Recall that the number of channels is also known as the number of feature maps, in case you are using different terminology. Because we usually have the kernel height equal to the kernel width, we can just specify it as a single number, which we usually denote k when we talk about it in math. If you wanted to have your kernel height different from your kernel width, you could also specify it as a tuple. In modern deep learning, most of the time you'll see kernels of size 3, although in the old days you'd also see kernels of size 7 and kernels of size 5. Notice how the size is typically odd. You'll be able to deduce why that is the case after the next lecture. So that takes care of the first three arguments. The last relevant argument for us is the stride, which controls the step size when you move the kernel across the input image. So why do we use conv2d and not conv1d or conv3d? As you know, color images are three-dimensional, height by width by color. Well, it's 2D because the color dimension of an image is not a spatial dimension. The signal doesn't flow in that direction. It's also possible to have 1D convolutions and 3D convolutions using the conv1d and the conv3d layers respectively. So for example, if you're looking at a signal that varies with time, that would be a 1D convolution. If you're looking at a video, for example, that would be a 3D convolution. That's because height and width are the first two spatial dimensions, and time is a third dimension. It's also possible to have objects that have three spatial dimensions, height, width, and depth. Instead of pixels, we have voxels. You might encounter these if you look at something like medical imaging data. By the way, you might be wondering where the word voxel comes from. Well, it's pretty obvious that it's analogous to the word pixel, but why? Pixel is actually a short form of the phrase picture element, and thus voxel is the short form of the phrase volume element. In any case, now we can say that we fully understand the conv2d layer, so we can move on to asking, how do we include this in a neural network? Let's now talk about the concept of inheritance. PyTorch models are all based on modules, and I've probably used that word a few times throughout the course without really explaining what they are. Well, a module is the base class that all other modules inherit from. Inheritance implies an is-a relationship. For example, the linear module, which is the first one we saw in this course, inherits from the module class. That means it is a module. Similarly, the ReLU module is also a module. Similarly, the sequential module is also a module. This might strike you as surprising because these three things are kind of very different from each other. So even though sequential looked like a wrapper around a list of modules, it was also itself a module. So when you combine a bunch of modules to build a model, that model is itself a module. This implies that when we create our own custom models, they are also going to be modules, and we are going to inherit from the module class. So when I said earlier that PyTorch is all about composing models from building blocks, well, modules are those building blocks. One interesting consequence of everything being a module and models being modules is that there's this hierarchical structure. The first model we saw in this course was just a linear module. Then we saw that we could stack linear layers together in a sequential object, which is a module of modules. That's also a model. Later, you'll see that we can repeat this pattern so that our model is a module of modules of modules. So what we've learned is that a module is a model, but a module of modules can also be a model, as can a module of modules, and so on. By taking the perspective that everything is a module, building complex things becomes easier, because you only have to look at your current level of abstraction, and no matter how high level that may be, you're still just working with modules. So why might we want to build a custom model instead of just doing what we've been doing so far? Well, sometimes we need to do an operation that is not a module. For example, you know that the interface between the convolution layers and the dense layers in a neural network is a flatten. So after all the convolutions and before all the dense layers, we must flatten the data so that it fits into those respective layers at the boundary between these two different kinds of layers. The output of a convolution is an image, while a dense layer expects an input vector. Now, although PyTorch does have a flattened layer, you might wonder, what if it didn't exist? Or what if some other operation you wanted to do didn't exist? In that case, you could build a custom model. In the case of flatten, we know that we can always just use the view function to reshape an image batch into a batch of vectors. In fact, not even 1 year ago, counting from the time this course was being made, there was no flattened layer in PyTorch, so you had to build a custom model. So you're lucky in that sense. Today, a flattened layer exists, which makes things easier for you, but at the same time, there are still many things you might want to do where there does not exist a pre-built layer for you. As a side note, I commonly refer to these objects as layers, even though in PyTorch they are technically called modules. Layer is a better visual term in my opinion, since a neural network is made of layers. It's just easier to understand and see it in your mind. So please don't get confused when I use the words layer and module interchangeably in the context of PyTorch. In any case, I hope it's clear why we need custom models. When we have all the layers or modules we need, and they all occur sequentially in our model, which is not always the case by the way, then we can wrap them up in a sequential, as we've been doing so far. But if we want to do something more complex, then we need to build a custom model that inherits from the module class. Introducing this idea early in the context of CNNs is nice, because it allows you to compare both approaches. The easy approach is to do what we've already been doing, which is to build a sequential model that wraps up all the layers we want to apply in sequential order. The less easy approach is to build a custom model. But doing it both ways allows you to see the equivalence between the two, and hopefully that makes building custom models less intimidating than it would be otherwise. In addition, it's also a nice history lesson, because less than just 1 year ago, you wouldn't have had this luxury. Okay, so let's start by looking at a simple model we've already seen, an ANN. Just to recap, the simplest ANN we can make looks like this. We have a linear layer, followed by a ReLU, followed by another linear layer. No final activation function is needed, as you know. So what does this look like if we wanted to build a custom model? So first, we define a class that inherits from nn.module. Inside the constructor, we define all of our submodules, or layers. These are the two linear layers and the ReLU. Notice that all the layers in the sequential model are still defined in the constructor of the custom model. We assign these two instance variables so that they can be accessed from other methods, specifically the forward function. As you can see, the forward function is where we actually apply the operations defined by the layers we created. This is just like the simple linear regression model. When we create the linear regression model, we say variable equals nn.linear. Then when we want to use that model to compute some output, we call that variable object as if it were a function. Similarly, inside the forward function, when we want to compute the output of each of those layers, we simply call the module objects we created in the constructor. As an exercise, I would recommend trying to implement your own version of the sequential object using what you just learned. This would be a great exercise to test your understanding of module inheritance and building custom models, so please give it a try. So at this point, I hope it's easy to see the correspondence between a sequential model and a custom model that inherits from the module class. The next thing we're going to do is apply what we learned to build a more complex model, specifically a convolutional neural network. As you can see, it's pretty much the same thing, just with more layers and different kinds of layers. As we discussed in the theory lectures, what we have is a sequence of convolution layers, followed by a sequence of dense layers. Conveniently, because everything in PyTorch is a module, we can wrap all the convolution layers in a single sequential object and all the dense layers in a second sequential object. That will make it easier to call each of the layers from inside the forward function. Instead of having to call each of the layers one at a time, since there might be hundreds of layers, we can just make a few calls to the sequential objects. In addition, note the view function in between the two sequentials. This helps flatten the data from an image into a feature vector. You'll realize something strange about the previous code, which is that I didn't specify the input size for the first linear layer. To be clear, this is not correct PyTorch syntax. I'm using this as a placeholder until I explain these concepts in a future lecture. Remember that in PyTorch, there is a level of redundancy when specifying the input size and output size of each layer. The input size of one layer must match the output size of the incoming layer. But in the case of convolution, how do we calculate the size of the first linear layer's input? The answer is we'll have to manually calculate the size of the image as it passes through each convolution. Then, when we flatten the final image, the feature vector dimensionality will simply be the product of each of the dimensions of the image. For example, 10 by 10 by 3 would become 300. To contrast with our custom model, I also want to show you how we would build a CNN using the newly created flatten layer, which allows us to make use of the sequential module. It's pretty easy to see that all the same layers appear, and the only thing that's different is that instead of explicitly calling the view function, we can use a flatten layer instead. There is, however, still this small issue of how we calculate the initial input size for the first linear layer. We'll discuss that in the next lecture, so just hold that thought for now. So what you may have assumed earlier is that building custom models is hard, so maybe it's just better to use the sequential method for CNNs. But in fact, they are nearly equal. In fact, the hardest part is figuring out this question mark. What is the initial input size of the first linear layer? And you can see that either way, whether you build a custom model or just use sequential, you still have to do this work. I want to mention one small addition we sometimes make use of in convolutional neural networks, which is dropout regularization. If you've studied machine learning before, you may have heard of concepts such as L2 and L1 regularization, which aren't really used that often in deep learning anymore. Instead, dropout regularization is used more commonly. My goal isn't to get in-depth about dropout in this course because I already have a course for that describes it in detail. Instead, I'll give you a one-line summary, which is that by dropping random nodes in a neural network during training, we make the neural network less dependent on any particular input feature, which helps to spread out the influence of each input. This is similar to what L1 and L2 regularization try to do. In PyTorch, using dropout is as simple as including a dropout layer and specifying the probability of dropping a node during training. Usually, dropout is used between dense layers, but not with convolutions. Sometimes you'll see them used in RNNs as well, which you'll learn about in another section. One interesting discussion I've seen pop up here and there is whether or not you should use dropout regularization in the convolutional layers. While the PyTorch API lets you do this, it might not necessarily be a good idea. Remember that convolution is pattern finding. It's looking for a specific stroke or edge. If you suddenly remove half the pixels from an image, is the stroke still visible? Can it still be considered the stroke that we are looking for? Personally, I lean more towards no, but I've seen a few people use dropout in their convolution layers. Even if it doesn't hurt, if it also doesn't help, then there's no point in using it. As always, I recommend experimentation over guessing, so if you're interested in trying it, I would strongly suggest doing so. As a final note for this lecture, I want to give you some foresight into why learning about how to build custom models is so useful. We went over one major reason previously, which is that you might need to build a model that contains operations which are not PyTorch modules. But so far, we've only seen one basic kind of neural network in this course, one that encompasses linear models, ANNs, and CNNs. That is, these models always have one input and one output, and each layer is stacked on top of the last. Have you ever considered, what if I want my model to have branches? This by definition is not sequential, so you can't use nn.sequential. What if I want my model to have multiple inputs? Same story. Can't use sequential because this is not sequential. What if I want my model to have multiple outputs? Same story. Can't use nn.sequential. Now you might scoff and say, I will never need these types of models. Lazy programmer is just showing off that he knows all these complicated things. But in fact, you are wrong. We will be looking at such models later in this course. In this lecture, we're going to fill in the missing detail from the last lecture. How do we calculate the dimensionality of the initial feature vector into the dense layers of a CNN? For this, we need to know about a topic called convolutional arithmetic. Basically, these are the concepts that allow us to calculate what the output size of a convolution will be given some input size, some filter size, and various options such as padding and strides. As a reminder, the reason why we need this is because PyTorch requires you to specify both the input size and the output size of each layer, even though we implicitly already know this information. What's weird is that these calculations are well defined, so there isn't really a great reason to require us to do them ourselves. Libraries such as Keras make things super easy by automatically inferring the input size of each layer, so you only need to specify the output size. The reason I mention Keras a lot is because Keras is usually a student's first introduction to deep learning. And even if you don't know Keras, you could easily pick it up in a few minutes, provided you have some base level of programming skill. So another great thing about Keras is that it allows you to pass in a string to specify the type of padding that is used for convolution. As a reminder, we generally have three modes of convolution. In valid mode, the output size is n minus k plus 1. In same mode, the output size is just n, the input size. And in full mode, which no longer exists by the way, the output size is n plus k minus 1. And remember that these are just the basic form of convolution with no strides. So you might think, well that's great, if I just use same mode for all my convolutions, then calculating the output size is super easy. But wait. Passing in the mode of convolution as a string exists only in Keras, not PyTorch. The reason I mention this is because it's a natural question to ask. Why not use same mode so that it's easy to compute the size of the image after each convolution? If we do that, then let's say we have an input image of size 32 that goes through 3 convolutions with a stride of 2. After the first convolution, the image shrinks down to 16. After the second convolution, it shrinks down to 8. And after the third convolution, it shrinks down to 4. Easy. Well, let's ask ourselves, how would we do the equivalent of same mode in PyTorch? Let's see. We have to specify this padding argument, which tells PyTorch how many spaces to pad the input image on each side. But wait, in order to specify this argument correctly, so that you achieve the equivalent of same mode, you need to do convolutional arithmetic to calculate the correct amount of padding. In other words, you still need to do convolutional arithmetic whether you have same mode or not. So there's no benefit to using same mode because either way, you still have to do convolutional arithmetic. In fact, this might be a little harder because you have to do convolutional arithmetic in reverse. The only good reason to use same mode would be if you really believe it benefits your model's predictions. Okay, so now you're convinced that there's no way out of doing convolutional arithmetic. In this course, it's not my goal to go in-depth about this topic. If you want to gain a better intuition about convolutional arithmetic, I've left a link to deeplearning.net in the file extrareading.txt, which leads you to a tutorial about convolutional arithmetic and how the calculations change when you have padding, strides, and so forth. It's pretty non-trivial. However, an easy way to get around this is to simply use the formula that PyTorch provides in their documentation. With this formula, you can plug in all your values and calculate the output dimensions. You don't need to understand convolutional arithmetic to use this formula, you just need to know how to multiply, add, and divide. Let's do a simple example to make sure you know how to use this formula. Since the formulas for both the height and width dimensions are the same, we only need to do one. Firstly, the concept of dilation is outside the scope of this course, and we will use the default value of 1. Next, let's assume we have padding equals 1, kernel size equals 3, and stride equals 2. Let's set h in to 32, which is common for deep learning image datasets. If we plug these values into our formula, we get 32 plus 2 times 1, minus 1 times 3 minus 1, minus 1, all divided by 2. Then we plus 1 and then take the floor. So that gives us 31 over 2 plus 1, which is 15.5 plus 1, which is 16.5. Then we take the floor of 16.5 and we get 16. So h out equals 16. Now it's easy to make mistakes with these, and I wouldn't be surprised if I did. So if you want to double check my work, please do. Alternatively, you could just implement this in code. You may have noticed something a little curious on the previous slide, which is that in the PyTorch documentation, the input size and the output size are specified as n by color by height by width. This is contrary to what we've been working with so far, which is datasets of size n by height by width by color. Why is there this discrepancy? Well, it has to do with the conventions of the library. Remember that when you're a programmer building a library, you have full control over how it works. So you get to decide what the conventions are, how you want to structure the data, and so forth. It turns out that some developers decided to put the color channel first, while other developers decided to put the color channel last. In our case, libraries such as Theano and PyTorch decided to put the color channel first. Libraries like OpenCV, TensorFlow, Matplotlib, and Pillow use the convention that the color channel comes last. Although OpenCV does other weird things like using the BGR color ordering instead of RGB. So it seems that putting the color channel last has now become more common. But PyTorch was built with the color channel first. We can't just switch it around one day and expect everyone to update their code. Therefore, PyTorch still uses the convention that the color channel comes first. This detail is hidden from you if you use utilities, such as those from the Torch Vision library. Since we haven't worked with color images yet in this course, we haven't had the opportunity to uncover these hidden details, but now we do. As you recall, if you inspect the data attribute of a dataset loaded in from Torch Vision, it gives you the untransformed version of the data. These will be n by height by width by color. But when you yield batches of data from the data loader, this data is transformed in whatever way is needed before it goes into the neural network. And so, when you inspect these batches of data, yielded by the data loader, you will see that they appear as n by color by height by width. So in fact, PyTorch still uses the convention that the color channel comes first, but it comes with interfaces that work with the more commonly used convention that the color channel comes last. At this point, we finally understand how to fully build a convolutional neural network in PyTorch. Now we're ready to outline the upcoming code. As usual, I'm going to repeat the steps of our analysis just to be sure. Step number 1 is to load in the data. For the following examples, we'll be using more difficult datasets, in particular Fashion MNIST and CFAR10. Fashion MNIST was designed to be a drop-in replacement for the MNIST dataset, which today is considered to be too easy for modern machine learning algorithms. One might consider it to be a solved problem. Thus, Fashion MNIST was born, and it was designed to be a standard benchmark just like MNIST, but with the goalpost further ahead. Just like MNIST, it's a dataset of 28 by 28 grayscale images, and it even has the same number of samples. The difference is that instead of simply handwritten digits, we have images of different types of clothing. For example, t-shirts, shoes, pants, and so forth. Your job is to classify these images into the correct category. The CFAR10 dataset is older, but more difficult. This dataset contains color images, so the data takes up more RAM, and the images are also a bit bigger, 32 by 32. It contains classes such as automobile, frog, horse, cat, and dog. You can already imagine that, with such tiny images, it might be very easy to mistake a cat for a dog or a dog for a horse. Step number 2 is to build a model. Luckily, we just discussed that in painstaking detail over the past few lectures. In case you forgot, we'll be using convolutional neural networks. Step number 3 is to train the model. Step number 4 is to evaluate the model. And step number 5 is to use the model to make predictions. Just like the ANN section, nothing here changes. These steps are model agnostic. As per my rule, all machine learning interfaces are the same. One new thing you'll learn about later on in this section is what to do if your dataset is too large to fit into memory, or if you want to augment your data. For example, we know that a dog facing left is a dog, but a dog facing right is also a dog. So should our CNN not be able to recognize both of these orientations as a dog? The answer is yes. We also know that deep learning loves data. The more data, the better. This is why deep learning has come to prominence in recent years. So data augmentation is a method of virtually adding more data without actually having it. We'll discuss this more later on, but for our initial example, we're going to keep things simple. So let's elaborate on step number 1, loading in the data. Luckily, both the datasets we'll be using for these examples are also included in Torch Vision. It's generally going to follow the same pattern as before. You can even probably try to guess the function names, and you might be right. For Fashion MNIST, we load in the data by calling torchvision.datasets.fashionmnist. For CFAR10, we load in the data by calling torchvision.datasets.cfar10. Nothing too surprising there. Inside the training loop, we can loop over the datasets in batches by using the data loader, which, you guessed it, looks exactly the same as before. So what changes? Other than changing the model and changing the data functions, nothing really. So this is a great time to remind you of my 2 rules. All data is the same, and all machine learning interfaces are the same. So just as a quiz, let's think about which of these steps will be the same and which will be different. First, the training loop. As you know, we'll be doing batch gradient descent. Will this be the same or different? The answer is the same. Next question. Let's consider evaluating the accuracy of the model. Will this be the same or different? The answer is the same. Next question. Let's consider plotting the confusion matrix given the model predictions and model targets. Will this be the same or different? The answer is the same. The only minor, non-trivial thing I want to highlight is that the classes are going to be encoded as integers from 0 up to 9 inclusive. But how do we know which integer corresponds to which class? For example, what if 0 is dress and 1 is t-shirt? Is that obvious? Of course not. I just did the easy thing and looked them up on the internet and hard-coded them as strings. This way, when we look at the misclassified samples, it won't say something like 0 is misclassified as 1, which doesn't really mean anything, but rather t-shirt is misclassified as dress shirt, which is more interpretable. In this lecture, we are going to look at a Colab notebook that does image classification using PyTorch with a convolutional neural network on the fashion MNIST dataset. This lecture is going to walk you through a prepared Colab notebook, although a very good exercise, which I always recommend, is once you know how this is done, to try and recreate it yourself with as few references as possible. As usual, you can look at the title of the notebook to determine what notebook we are currently looking at. Alright, so let's start by recognizing everything that should seem familiar. First, we have all our imports. There should be nothing unexpected here. Notice how we're also importing the datetime module. This is useful since as your data grows and your models grow, training is going to take longer and longer. When training starts to take a non-trivial amount of time, we naturally start to ask, so how long is this taking? And so we can use the datetime module to get a sense of how long each iteration of the training loop takes. In more high-level libraries like Keras, this all happens for you. But in PyTorch, if you want these features, you have to build them yourself. Next, we load in the data, which is, as we mentioned, the fashion MNIST dataset. Since it's included in the Torch Vision library, nothing has to change in the way we load in this data. Next, we're going to check a few of the dataset's attributes to see how it compares to MNIST. Remember, it's supposed to be a drop-in replacement. As you can see, the maximum value is 255, which is what we expect. The shape of the data is 60,000 by 28 by 28, which is what we expect. And the targets contain integers that look like they're between 0 and 9 inclusive, which is also what we expect. Next, we load in the test dataset, and then we get the number of classes by casting all the targets into a set and then taking the length of that set. As expected, the dataset contains 10 classes. The next step is to define our CNN model. As promised, we're going to start looking at how to build models using inheritance rather than stacking layers together in a sequential. On the first line, you can see that the CNN class inherits from the nn.module class. This makes our class an official PyTorch module, meaning it has all the useful functions and attributes that a built-in PyTorch module has, even doing automatic differentiation. Inside the constructor, the first thing we do is call the parent class's constructor. Next, we create our layers. The first set of layers is a series of convolution layers, followed by the ReLU activation function. We can wrap this in a sequential to make it easier to call in the future. Notice that the first convolution layer has only one input channel. That's because, as you know, the MNIST and hence fashion MNIST datasets are grayscale. As you recall, we need to do some convolutional arithmetic in order to calculate the arguments into the first linear layer. So I've left some useful links here on this topic if you want to check them out. I would recommend you do the calculation yourself to make sure that what I've written below is correct. Next, we have a series of dense layers, along with some dropouts and a ReLU activation. Again, we wrap this in a sequential, so it's easier to call later. Next, we have the forward function. This is where we actually pass a given input through the CNN to get the neural network's output. As you can see, it's made up of just 3 lines of code thanks to our sequential objects. First, we pass our input into the convolution sequential. Next, we reshape those outputs in order to flatten them using the view function. Notice how there's no need to specify both dimensions of the flattened output. However, it may be easier to specify just the first dimension and not the second one. The first dimension simply refers to the batch size, which we can obtain by using out.size of 0. This is because if we have n samples in, we also must have n samples out. Clearly, the number of samples we pass into the input of a neural network must also be the number of predictions that we get out. The -1 means that PyTorch will automatically calculate the leftover dimension given whatever dimensions are left. Next, the third step is to pass the data through the dense layers, and finally we return the output. The next step is to instantiate the model. We pass in one argument into the constructor, which is the number of classes k. In the next block of code, I show you how to build an equivalent CNN using the sequential module instead of building a custom class. As you can see, it's much simpler, but still requires you to do convolutional arithmetic to determine the first linear layer's input size. You might want to try both models and confirm that they are equivalent. The next step is to move our model to the GPU, which you already know how to do. The next step is to create our loss and optimizer, which you already know how to do. The next step is to create our data loaders, which again, you already know how to do. The next step is to create our training function, which again, you already know how to do. The only minor difference here is that I have some timing code, and when each epoch completes, I print the duration of that epoch. So you can see here I'm printing out the epoch duration. But now you see how important it is to understand what we were doing previously. We'll be seeing that exact same code again and again. Alright, so training completed successfully at around 6 seconds per epoch. Next, we plot the loss per iteration as usual. So this appears to look good. Next, we get the train and test accuracy using the same code we saw before. As you can see, we do pretty well, about 94% on the train set and about 89% on the test set. But this is definitely less than the accuracy we got on the original MNIST dataset. Next, we have our confusion matrix code. So if we scroll down, we can see what our model is most confused by. Unfortunately, the axes are labeled with integers, so it's hard to tell what's what. But we can see if we look at the labels below what each of them means. So it seems we often confuse 0 with 6 and 6 with 0. 0 corresponds to t-shirt and top, while 6 corresponds to shirt. So it definitely makes sense that our model would confuse these. In fact, one might argue that they are the same thing, and that even humans would confuse these. That's similar to what we saw with MNIST. We can also see that 6 gets confused with 4 a lot. As we saw, 6 means shirt, and now we can see that 4 means coat. This also makes sense, given the very low resolution of the images. Basically, they're little white blobs on a black background. We would expect that a coat has a similar shape to a shirt. We also see that 2 gets confused with 4 and 6 as well, pretty often. 2 stands for pullover, which again is pretty much a shirt, especially when it's just a 28 by 28 blob. On the other end of this, we see that 7 often gets confused with 9 and vice versa. 7 corresponds to sneaker, and 9 corresponds to ankle boot. So again, considering that the images are just little blobs, this makes total sense. Let's now look at some misclassified samples to check if our reasoning holds. So the first one we see is a t-shirt top getting predicted as a shirt, which makes sense. Here's a shirt predicted as a pullover. That makes sense. Here's a shirt predicted as a coat. I wouldn't really consider that to be a coat. Here's a t-shirt predicted as a shirt. That makes sense. Here's a pullover. I think we saw this one. Here's a sandal predicted as an ankle boot. That makes sense. Here's a coat predicted as a pullover. That makes sense. So you can see that all the things that are getting misclassified are generally the same. Okay, so as a final exercise for this lecture, what you should try is mix and match the models and data that we've seen so far. Previously, we used an ANN on MNIST, and now we're using a CNN on Fashion MNIST. You should have some intuition that a CNN should perform better than an ANN, but also that Fashion MNIST is a harder classification problem than MNIST. So what will happen if you try to use an ANN on Fashion MNIST? What kind of results do you expect to see? What will happen if you try to use a CNN on MNIST? What kind of results do you expect to see? As always, remember my rule: machine learning is experimentation and not philosophy. Whenever you want to know the outcome of running some computer code, never try to guess the outcome with your mind. Well, in this case, it's okay because I've asked you to, in order to check whether your intuition is correct. But what you really want to do is write these scripts in code and see the answer for yourself.